Okay, so now we're going to take a look at using the trig rule there. So combine up what you know so far. See if you can find those first three derivatives. Okay, it sounds like you've got them. For the first one, you should get 2 cosine x. For the second one, you could write this either as 1/2 cosine x, or it would be fine to call it cos x over 2. Those are the same thing. For the last one, 1 minus sine x. Okay? And now, it is time for your favorite derivative. The derivative of all derivatives is the natural exponent. And I'm not being sarcastic here. It will be your favorite derivative. And here's why.
Oh.
So, boy, wasn't that Euler clever. He found something interesting. The function has the same value as its derivative. So you'll like this one because you do need to know it, of course, but there is no change. E to the x stays as e to the x. Okay, so now wrap them all together. You got polynomials, you got exponentials, and you got trig graphs in there. See if you can figure out those derivatives. Okay, so this one should be even faster, right? Because, I mean, this one is, oh yeah, there we go, perfect. Right, no problem. 2x plus my favorite derivative, and this will be cos x minus my favorite derivative. Okay? So we talked a little bit about average velocity earlier in the block, and it's a good segue to today's class. When we're talking average velocity, we're talking about 2 points. And, of course, when we find a slope with 2 points, we're talking about a secant line. So I'm going to show you the difference here between the secant line and the tangent line with a couple examples. We'll look at some application sort of things. So for the first one, this is the world that you were in before you came to calculus. Isn't that a happy place? How many people wish they were still there? Yeah, fair enough. Okay. Me too sometimes. So this time, a billiard ball, that's a pool ball, is dropped from a height of 100, and I'm guessing feet. So 100 feet, its height, h, at time t, is given by this formula. So if I wanted to know the height at 1 second, I can put in 1 second for the time. It will tell me the height. Okay, so the ball is falling right now. So we want to find the average speed that it's traveling from the first second to the second second. Okay? So first of all, what we have to do then is we want to figure out the change in height divided by the change in time. That will give me its average speed. So how could we do that? What would the average height be? Well, we'd have to stick in -16 times 1 squared plus 100. And I believe that's, is that going to be 84? And then -16 times 2 squared plus 100, and I think that's 36. Okay. So if I use my slope formula, that'll be at 1 second it would be 84, and 2 seconds 36. So here's my change. And the time went from 2 seconds to 1 second. So over that time period, its average speed was -48 feet per second. Do you think that, you know, I mean, it's only 1 second, so it probably was 48 feet per second in there, or, you know, most people would think for a little while. But it probably was only -48 feet per second one time in that whole interval, right? It would have been slower at 1 second and faster at 2 seconds. So -48 feet per second doesn't really tell us what happened in the middle. Okay? Why is it negative? Going down, right, physics people? It's falling, so it's negative. So the other way you can think of this is your rate of change. This is a rate of change. When the rate of change is negative, it's decreasing, so it's going down. It went from 86 to 36. It's a decreasing value. Okay? Again, it's important you try and say that in your head, even when I'm not. Okay? This is a rate of change that's negative, so it decreases. It went from, this is 1 second, this is 2 seconds. It lost about, I don't know, what's that, 48 feet in that time. So, again, that's, you know, that's okay, but we can do better. Anybody been to Canada Games Pool? A pool that has a 10-meter diving board? Okay, apparently there's more than just Canada Games Pool now. So when I used to work there, we would jump off this thing, and the first time I tried to dive, I went like this, and I dove like a regular dive. And of course, I'm going so fast that when I hit the water, my head went like this, and it basically glued itself to my shoulder. And luckily, I was 18, and my neck was really rubbery back then, and it didn't really hurt myself. But just so you know, you're supposed to hold your hands like this and glue your ears to your head. I had a diving friend taught me how to do it properly. But the point is, you're going pretty fast when you hit that water, right? How fast are you going? Well, we can work it out. Here is the model that shows me the height of a diver that drops from 32 feet, which is about 10 meters. Okay, so if anyone's jumped off this 10 meter and you're kind of like, wow, how fast am I going when I hit the water? Well, that's one instant when you touch the water, and that's what we'd like to find. So the first thing is, when do we hit the water? How could we figure out what time we hit the water? What about 0? Like 0 seconds? Height is 0. Right, so that's our first task, is we need to figure out when is the height equal to 0. So to do that, I'm going to end up factoring some stuff. That's going to be t squared minus t minus 2, which will be negative 16 t, let's see here, minus 2 and t plus 1. So I get time is equal to either negative 1 or 2. So what do you think? Does that mean you jumped off the diving board backwards if you went at negative 1 seconds? No, we would just reject that. It doesn't make sense, right? It's before we started this experiment, so it doesn't happen. This person falls from the diving board, they hit the water 2 seconds later. So the question is, if this is the function that tells us how high up they are, we can use that to figure out the change in their height at an instant. So this is the instantaneous rate of change, right, in the height. Change in height over change in time, that's a speed. So this will be negative 32 t plus 16. The time that I'm interested in is the 2 second time. So this will be at 2 seconds, negative 32 times 2 plus 16, which is negative 48 feet per second. Okay, so this person that is falling, so it's a good thing they have a negative rate of change. Otherwise, they've defied the laws of gravity and somehow they jumped off a diving board and ended up going through the roof, right? They're falling, so it's negative 48 feet per second, and that's the instant they touch the water, okay? Don't try it with concrete, but it's safe to do it with water, okay? If you hit the water at 48 feet per second, you're okay. So my challenge for you now is to dispel a little urban myth. And here's the urban myth. I don't know if you guys have heard this one, but people have told me if you're in an elevator and it starts, the brakes give out and you start to fall, right? All you have to do is watch the numbers as they tick down, and right before you hit the lobby and you get squished, you just have to jump. And as soon as you jump, that'll cancel the speed of the elevator out with your jump, and you'll be safe, right? People actually think these things, but let's just see. Is this actually, I mean, I'll give you this. If you fell from like if the elevator fell like 5 or 6 feet, yeah, you could probably get away with it. But most elevators are a lot higher up than 5 or 6 feet. Otherwise, you just take the stairs. So let's say you're on the 10th floor. It's 100 feet up. How fast would you have to jump to cancel out the elevator speed when it hits the ground? Now I'm going to give you the model. This is the model for something that starts with initial velocity 0. So the cord is cut. It falls from a height of 100 feet. And obviously there's some physics involved here. You might recognize kind of this formula, but this is actually the formula that the elevator will fall by. Okay, so see if you can figure out when it touches the ground, how fast is it going? That means you'd have to jump. Like if it's going 30 feet per second, you'd have to jump at 30 feet per second. Okay, so see if you can figure out how fast would you have to go. Okay, so I think most of you are getting there. First we got to figure out when you're going to hit the ground, which is at when the height equals to 0. So this is, whoops, I have to see why my pen's not working. See if this one works. Okay. Nope. Okay, so I'm going to finish this question. I realize most of you got there while we had those technical difficulties. But to find out where the height equals to 0, that's when it's going to touch the ground in this case. So if I solve this, that'll be negative 100 equals negative 4.9 t squared. So t is going to be the square root of 100 over 4.9. And that's the time that it hits the hits the ground, the elevator. Now I need to figure out its speed when it hits the ground. So the derivative of the height, meaning what's the change in the height, the speed at which this object is falling, the elevator is crashing to the earth, that will be negative 9.8 t. And the time that I'm going to use is the one when it hits the ground. I could find it any way on the way to the ground, but that's the one I'm interested in. So negative 9.8 times the square root of 100 over 4.9. And of course you're going to need a calculator for that, unless you can do square roots in your head. So I get 100 divided by 4.9, and its square root times 9.8. Sorry, so I get negative 44.3 feet per second. So you'd need to be a pretty, I don't even think it's humanly possible to jump that fast, but anyways, stick to elevators that are only, say, 2 or 3 stories. You'll probably be fine either way if you jump or don't. Oh, just so everybody knows and they don't have nightmares, there's backups on elevators. If the cable breaks, there's brakes, so don't.